Today we explore one of the most profound discoveries in early quantum physics, Peter Debye's revolutionary theory of heat capacity in solids. This lecture examines how Debye solved the mystery of why heat capacity in crystals behaves so strangely at low temperatures, leading to groundbreaking insights about quantum vibrations. Let's begin by understanding what puzzled physicists in the early 1900s. According to classical thermodynamics, the heat capacity of solids should remain constant at all temperatures, equal to 3 times the gas constant per mole. This is known as the Dulong Petit law, where heat capacity equals 3R, approximately 25 joules per mole Kelvin. However, careful experiments in the late 1800s revealed that heat capacity actually drops towards zero as temperature approaches absolute zero. Here we see the classical prediction in red stays flat, while experimental data in green shows heat capacity rising from zero at low temperatures. This dramatic disagreement represented a fundamental crisis for classical physics, suggesting something deeply wrong with our understanding of matter. Before Debye, Einstein made the first quantum attempt to explain this anomaly. In 1907, Einstein proposed that all atoms in a crystal vibrate at a single characteristic frequency, treating them as quantum harmonic oscillators. The average energy of each oscillator is h bar omega over E to the h bar omega over kBt minus 1 from quantum statistics. This leads to Einstein's heat capacity formula, which successfully predicted the drop at low temperatures. While Einstein's model captured the general trend, it didn't match experimental data precisely, especially at very low temperatures. At very low temperatures, experiments showed heat capacity follows a T³ law, but Einstein's model predicted exponential decay. Now we arrive at Peter Debye's brilliant contribution in 1912. Debye's key insight was that a crystal doesn't vibrate at just one frequency, but has a continuous spectrum of allowed vibrational modes. Think of a crystal like a complex musical instrument with many different vibrational modes, from low-frequency acoustic waves to high-frequency optical modes. Debye modeled the crystal as an elastic continuum, treating vibrations as sound waves or phonons propagating through the material. The density of vibrational states grows as omega squared, where omega d is the Debye cutoff frequency containing 3 n total modes. The spectrum extends from zero frequency up to the Debye cutoff frequency, determined by the total number of atoms in the crystal. Debye introduced a characteristic temperature that governs the quantum behavior. The Debye temperature theta d equals h bar omega d over kb, setting the scale for quantum effects in the crystal. Different materials have different Debye temperatures. Diamond has a very high value of 2230 Kelvin, while lead is only 105 Kelvin. Materials with strong, light bonds like diamond have high Debye temperatures, while heavy elements with weak bonds like lead have low values. When the actual temperature is much less than the Debye temperature, quantum effects dominate. When T is much greater than theta d, classical behavior emerges. Now let's derive the complete Debye heat capacity expression. The total energy is the integral over all frequencies of the quantum oscillator energy times the density of states. After differentiation and change of variables, we get the Debye heat capacity with a temperature-dependent integral called the Debye function. This remarkable formula correctly describes heat capacity from absolute zero to room temperature and beyond, using just one parameter, the Debye temperature. Let's examine what happens at very low temperatures where quantum effects dominate. When temperature is much less than theta d, the upper limit of the integral effectively becomes infinite, and the integral evaluates to a constant. The definite integral equals 4 pi to the 4th over 15, approximately 26.0. This gives us the famous T³ law. Heat capacity is proportional to temperature cubed at low temperatures. At low temperatures, this cubic dependence matches experimental data beautifully, explaining the anomaly that puzzled physicists. The T³ law arises because at low temperatures, only the lowest frequency acoustic phonons have enough thermal energy to be excited. Now let's see how classical physics emerges at high temperatures. When temperature greatly exceeds the Debye temperature, quantum discreteness becomes unimportant, and classical behavior emerges. In this limit, heat capacity approaches the classical Dulong Petit value of 3 nkb, or 3R per mole. This demonstrates how quantum mechanics smoothly transitions to classical physics at high temperatures, a requirement of the correspondence principle. The heat capacity curve rises from 0, following T³ initially, then smoothly approaches the classical limit of 25 joules per mole Kelvin. Now we examine Debye's ingenious method for analyzing experimental data. Debye realized that if you divide heat capacity by T³ and plot against temperature, something remarkable happens at low temperatures. At low temperatures, this ratio should approach a constant value equal to 12 pi fourth over 5 times nkb over theta d³. When plotted this way, experimental data shows a nearly flat plateau region at low temperatures, beautifully confirming the T³ law. The Debye plot shows a flat region at low temperatures, then drops as temperature increases beyond the Debye temperature. The height of this plateau directly gives us the Debye temperature for the material, providing a clean way to extract this fundamental parameter. Let's understand the physical nature of these quantized vibrations called phonons. Just as light consists of photons, crystal vibrations consist of phonons, which are quantized packets of vibrational energy. A phonon represents a coordinated wave of atomic displacements traveling through the crystal lattice. Each phonon carries energy h-bar omega, where omega is its frequency. Acoustic phonons are low-frequency modes where neighboring atoms move together, like ordinary sound waves. Optical phonons are higher-frequency modes where neighboring atoms move in opposite directions. You might ask, why is understanding heat capacity so important? Heat capacity determines how much energy a material can store, crucial for thermal management in everything from engines to electronics. The temperature dependence of heat capacity provides direct evidence of quantum mechanics operating at the atomic scale. Understanding heat capacity is essential for cryogenics, designing superconducting systems, and all thermal engineering applications. Debye theory underpins technologies from cryogenic cooling to superconductivity to thermal management systems. Let's work through a concrete numerical example using silver. Silver has a Debye temperature of 225 Kelvin, making it a good example for calculations. At 10 Kelvin, we use the low temperature formula. The ratio 10 over 225 cubed gives us the scaling factor. This gives approximately 0.234 joules per mole Kelvin, vastly below the classical value. At room temperature of 300 Kelvin, which exceeds theta d, silver's heat capacity approaches the classical value. At 300 Kelvin, heat capacity is about 24.5, nearly equal to the Dulong Petit value of 25. Let's directly compare the Einstein and Debye approaches. Einstein's single-frequency model gives exponential decay at low temperatures, while Debye's spectrum gives the correct T³ behavior. The Debye model is more physically accurate and matches experiments better, though Einstein's simpler model captures the essential quantum nature. Both models were revolutionary because they demonstrated that quantum mechanics is necessary to understand even simple bulk properties of solids. The Debye model has limitations that led to further developments. The Debye model treats the crystal as a simple elastic continuum, ignoring the detailed atomic structure and directional properties. In reality, sound velocity varies with direction in crystals, leading to more complex phonon dispersions than Debye assumed. The Debye dispersion is linear, while real phonon dispersions show curvature and cutoffs at Brillouin zone boundaries. Modern computational methods calculate exact phonon dispersion relations from first principles, going beyond the Debye approximation. Debye's work had profound impacts on physics and earned him the Nobel Prize. Peter Debye received the 1936 Nobel Prize in Chemistry for his contributions to understanding molecular structure, including this heat capacity theory. The Nobel Committee recognized how Debye's theory unified quantum mechanics with thermodynamics and solid-state physics. This work established phonons as fundamental quasi-particles in solids, analogous to photons in electromagnetic fields. Debye's theory laid the foundation for modern condensed matter physics, influencing everything from superconductivity to thermal transport. The concepts from Debye theory connect to many other physical phenomena. Thermal conductivity in insulators occurs through phonon transport, where quantized vibrations carry heat energy through the material. Thermal conductivity kappa equals 1/3 times heat capacity times sound velocity times phonon mean free path. In conventional superconductors, phonons mediate attractive interactions between electrons, leading to Cooper pair formation. Two electrons can attract via phonon exchange, forming Cooper pairs that underlie superconductivity. Modern experiments probe phonons directly with remarkable precision. Inelastic neutron scattering allows us to directly measure phonon energies and momenta throughout the Brillouin zone. Raman and infrared spectroscopy techniques directly measure optical phonon frequencies in crystals. A neutron scatters from the crystal, exchanging energy and momentum with phonons, revealing the complete phonon spectrum. Remarkably, these modern experiments confirm that Debye's simple theory accurately describes low-energy phonons in most materials. The mathematics behind Debye theory involves quantum statistical mechanics. Phonons are bosons, meaning any number can occupy the same quantum state, following Bose-Einstein statistics. The average number of phonons at frequency omega is given by the Bose-Einstein distribution, 1 over e to the h bar omega over kBt minus 1. At high temperatures, many phonons occupy each mode, approaching the classical limit where kBt much greater than h bar omega. At low temperatures, only the lowest frequency modes have significant phonon occupation, explaining the T³ heat capacity. The Bose-Einstein distribution shows exponential decrease with frequency, with high occupation at low frequencies and low occupation at high frequencies. You might wonder, does Debye theory apply to metals as well as insulators? In metals, conduction electrons contribute an additional term to heat capacity, proportional to temperature, not T³. Total heat capacity in metals is gamma T from electrons plus beta T cubed from phonons. This equation correctly accounts for both electronic and lattice contributions to the total heat capacity of metals. Let's summarize the key points from our exploration of Debye's theory. Debye's theory provides a quantum mechanical explanation for the heat capacity of solids, resolving a major puzzle in classical physics. The theory is based on the idea of phonons as quantized lattice vibrations, which are the fundamental excitations in solids. The Debye model has been incredibly successful in explaining experimental data, and it remains a cornerstone of condensed matter physics. Debye's theory has had a profound impact on our understanding of solids, and it continues to be an essential tool for understanding the behavior of materials.